Welcome to Chemistry 312, Radiochemistry. This is the first part of Lecture 1, and it is the course overview. In this lecture, we're just going to discuss the class organization, the outcomes of the course, and how the course will be graded. Radiochemistry is central to a range of nuclear technologies. This is going to be emphasized in the course. We're going to explore the fundamentals of radiochemistry and show how those fundamentals extend into nuclear applications. Some of these nuclear applications are shown here. One of importance is the nuclear fuel cycle, where radiochemistry is involved in the uranium source, as well as the production of the uranium fuel. The radiochemistry involved in nuclear reactors will be discussed. For most reactor systems, existing light water reactors using uranium dioxide as fuel, the chemistry is fundamentally confined to the fuel region, whereas in some reactors under exploration, molten salt reactors, chemistry is central to the behavior of these systems. We'll explore radiochemical separations, which greatly leverage radiochemistry, and how these separations involve both the fuel cycle and application of isotopes. We'll talk about radioactive waste forms, how radioactive waste is disposed, and where chemistry and radiochemistry comes into play. We will also discuss nuclear forensics and safeguards. The role of radiochemistry in both these areas is important in the prevention of proliferation. We'll also extend this discussion to radiopharmaceuticals, the use of radioactive isotopes for medical applications, and the important role radiochemistry plays in that in both the production of the isotopes, the separation and purification of the isotopes, and how the isotope is bound into the pharmaceutical to create the radiopharmaceutical. And we'll also discuss fundamental science, where radiochemistry is germane to understanding technetium and the actinides, as these elements are only available as radioactive isotopes. The emphasis of this course is really to interest students in radiochemistry. Ideally, this course will provide a route for research opportunities for students in radiochemistry. This includes the UNLV Radiochemistry program, which is an active PhD-based program, but certainly has opportunities for undergraduate students to perform radiochemistry research in campus laboratories. An example of some ongoing research in the UNLV Radiochemistry laboratories is shown here. This solution is an ionic liquid. Uranium hexafluoride has been introduced into the ionic liquid. The uranium undergoes reduction, forming uranium-5 and uranium-4 compounds. Some unique capabilities of the UNLV radiochemistry program allow the studies with uranium hexafluoride. It is very unusual for a university to have this capability. There are also national laboratories, a number listed here, that have a strong interest in radiochemistry and provide opportunities for students to continue learning about radiochemistry or even be employed and practice radiochemistry. A number of these laboratories will be visiting the campus later this year, and we will provide an opportunity for the course to attend the lectures from this visit. The course includes the physics of radioactive decay and the chemistry of isotopes. Fundamentally, radiochemistry is at the intersection of the periodic table and the chart of the nuclides. The periodic table has structure, as chemists, that one understands, that are based upon the electrons, whereas the chart of the nuclides has structures and describes properties that are based upon how the nucleons, the neutrons and protons, are engaged in the nucleus. So periodic table, electrons, chart of the nuclides, neutrons and protons within the nucleus. And within radiochemistry, we want to emphasize elements with only radioactive isotopes, since they're unusual examples. So as examples, technetium, element 43, sits in the middle of the periodic table. We'll discuss the chemistry of technetium, and we'll particularly focus on the chemistry of the actinide elements, which are those elements that have 5f electrons that are at the bottom of the periodic table. The course topics includes the chart of the nuclides, details on alpha decay, beta decay, gamma decay, and fission. You should understand what the differences are in those by the end of the course. Methods and data that are obtained from investigating nuclear properties. We'll have discussions on the fundamental chemical properties that are involved in radiation radiochemistry, and particularly how they intersect with the elements that are only available in radioactive isotopes, such as technetium and particularly the actinides. We'll discuss how isotopes are produced, and we'll talk about how radiochemistry is used in research and technology. The textbooks that will be used in this course are primarily PDFs, and they'll all be linked to the Canvas website. The two textbooks that we'll use include Nuclear and Radiochemistry and Modern Nuclear Chemistry. And one thing that I want to note is that input from students are valued for this course. Participation is expected, and any sort of assistance with course development is valued. And the output obtained from the students should enhance the online course experience. The course has 7 outcomes where by the end of the course, the student should have some expertise, experience, knowledge in a few different topics related to radiochemistry. First outcome is understand, utilize, and apply the chart of the nuclides, table of the isotopes, to radiochemistry and nuclear technology. Primarily, this is understanding how to obtain the data that are presented in those documents and utilize that information. Another thing the students should understand is the structure of the nucleus. Often in chemistry, we ignore the nucleus, but within this course, we do want to investigate the fact that the nucleus has structure. Here, there's an example of an oblate, spherical, and prolate nuclei, and we will discuss within the course how this structure is understood and what's the relationship between the shape of the nucleus and some behaviors that are observed. Another aspect of radiochemistry that should be understood is the chemical properties of radioelements. Those elements that are only found as radioactive isotopes. They include the actinides, which are filling 5f electrons, and then technetium and promethium, which are elements that are normally found in the stable region, those elements below 83 protons, but are in fact radioactive. The students should also be able to comprehend and evaluate nuclear reactions and how isotopes are produced. This can be obtained and understood from using the chart of the nuclides. One can evaluate certain reactions. So for instance, here's a reaction shown here of a proton and nitrogen 15 makes oxygen 16. There's an alpha particle decay that makes carbon 12. That's in an excited state. It gives off a photon. Now it makes a ground state, carbon 12. The course will describe not only understanding how the particles and the isotopes react together, but the probabilities of those reactions. And that'll include cross-section data, understand what are some of the reaction particles. So for instance, an alpha particle, how that can be a product or can also be involved in a reaction. And then energies in the reactions. Where do these energies come from? Well, a lot of it comes from conversion of the mass from the starting compounds to the product. And we should also explore and understand the different types of radioactive decay. And by evaluating the chart of the nuclides, understand the location of the isotopes and what's the probability of a certain decay coming from those isotopes. For instance, heavier isotopes tend to decay by alpha. Those isotopes that are proton rich tend to decay by positron or electron capture. Those that are neutron rich tend to decay by beta minus. And then we'll discuss relationships between half-life and decays. The course will also describe how radiochemistry can be used in research, how as an example, concentrations, very minute concentrations down to femtomolar per liter or even less of isotopes can be measured. My thesis work, I studied one atom at a time chemistry, so one can do incredibly small concentrations. And we'll describe how these concentrations can be evaluated and how isotopes, making radioactive isotopes of normally stable isotopes, can be used to expand our understanding of systems. And finally, the course will investigate modern topics in nuclear and radiochemistry. This will be brought in the lectures, in discussions, and then in the final we'll have presentations, papers, and employment opportunities, which will hopefully link together what was learned in the course where radiochemistry is going today.
Information on the course grading is provided here. At the end of each lecture, there will be a short quiz. The quiz will be based upon the presented information and provided on the Canvas site. Each quiz is worth 1 point, so there will be 18 points from these post-lecture quizzes. There are 4 comprehensive celebrations of learning in the course. These celebrations of learning are take-home, and they are based upon the information provided in the lectures. They'll be posted, and the first due date is generally 5 days after the posting. The answers will be provided after the end of the first due date, and a second submission will be allowed to correct errors at 50% of the initial grade. You'll usually have 3 days for the second submission. The goal of the quizzes is to demonstrate material comprehension. Therefore, these resubmissions are allowed so the student can demonstrate understanding the material. Each celebration of learning is worth 15 points. The final, worth 20% of the total grade, will be a review of a paper, a review of a presentation, and a review of a radiochemistry position. You'll be asked to discuss the paper and the presentation, highlighting topics and information that was obtained during the semester. Class participation will make up the remaining 2% of the grade, and this will be based upon responses to discussions on the Canvas site, participation in office hours, course meetings, and Canvas interactions. Obviously, in-person attendance always increases class participation. However, the participation will also be gauged through the interface with the Canvas site. There is also the potential for more points to be gained through extra credit and guest presentations that may occur during the semester.
The course topics are provided here. We'll start with nuclear data, discuss nuclear properties, go on through equations that describe the kinetics of radioactive decay, evaluate different decay routes, discuss nuclear structure models and nuclear reactions, evaluate the interaction of radiation with matter. Then the lectures will begin to cover chemistry, starting with understanding chemical forms, then specific lectures on the chemistry of the early actinide elements, then move on to some applications of this chemistry in reactor fuels, separations, specific applications related to nuclear batteries and radiopharmaceuticals, and finally end on nuclear forensics. The course agenda is shown here. The lecture number and topics are provided with the dates in which they're posted and the dates in which they're due. The class meetings on Zoom will also be indicated. The dates for the celebrations of learning are provided, again showing dates posted, due dates, and when the second due date for the celebration of learning is. Spring break should be noted, as well as the finals week.
This concludes the orientation for Radiochemistry 312, overviewing the class organization, the outcomes, and the grading. When you have completed this section, please continue on to the first materials lecture for Lecture 1, which will highlight nuclear data. And this nuclear data will be presented initially and be repeated frequently throughout the semester.